States what is meant by the principal focus and the power of a converging lens. Now, it's a state question here. There are 2 marks up for grabs. You just need to know 2 different definitions and then write those down. So firstly, principal focus. Now, it's quite difficult to describe principal focus without drawing a diagram, but basically when light rays pass through a lens, they will all focus at a certain point. They could focus all at different points, but the principal focus is the point where the light rays which were originally parallel to the principal axis will focus to. So if you imagine sort of light rays coming in horizontally, so you can see they focus at a certain point. If the light rays were traveling at any other direction on the way in, then they would focus at different points. So you could call that the principal focus there. Quite useful in telescopes, for example. So let's write our definition down. So quite a wordy definition there, but you can see that the light rays pass through. If they're parallel, then after they pass through the lens, they will cross over at the principal focus. And that principal focus has to be on the principal axis. Not got a lot of room left for the second definition, but let's write it in anyway. So power is equal to 1 divided by focal length, and that's measured in meters to the power of -1. So it's a 2-mark question. You'll get 1 mark for each of those points. Complete the ray diagram below to show the formation of an image of a real object O by a diverging lens. Label the image clearly. Now for this kind of arrangement, we're going to get an image on the left-hand side of the lens. So let's start drawing our rays, starting with the horizontal ray coming from the top of the object towards the lens. Now this diverging lens is going to send that ray going upwards. If we just quickly draw an arrow on that ray as well before we forget. We need to know the exact direction that ray is going to go up, and the way that we work that out is we start by drawing a line which starts at the focal point on the left-hand side and passes through the point of contact with that initial ray and the lens. Now what I should do at this point is turn this diagonal line on the left-hand side of the lens into a dotted line to show that it's not actually the path of the ray. So as you can see, that ray is now diverging upwards. The next ray that we want to draw is from the top of the object through the center of the lens diagonally downwards. And that ray just continues in a straight line. Now the point that we're interested in is the point where that diagonal line that I've just drawn and the dotted line cross over, because that's going to be the position at the top of the image. Now, similar to how the object is drawn, we're going to draw an upwards arrow to represent the image. And then we need to make sure that we label this image as well. And as you can see from this diagram, the top of the image is the point where the 2 outgoing rays on the right-hand side would have crossed if there was no sort of lens involved. So in terms of mark allocation, you get the first mark for correctly drawing one of the 2 rays, doesn't matter which one. And then the second mark requires a bit more work. Firstly, you need to correctly draw the second ray. You also need to draw the image correctly and label it, as I've done. So 2 marks there. States the defect of vision that will be corrected using a diverging lens. Now, anyone that's familiar with sort of opticians and things like that will know that if you're using a diverging lens, which is kind of concave in appearance, that's used to correct short-sightedness. And then the opposite of that, a converging lens, which is convex in appearance, will be used to treat farsightedness. You could also write the word myopia, that's fine. They've given us quite a lot of space to write this answer in, but it's just a case of remembering the correct term and writing it down. So just the 1 mark for that. A diverging lens of focal length minus 0.33 meters is used to view a real object placed 0.25 meters from the lens. Calculate the distance from the lens to the image. So let's first of all write down the equation that we're going to use to calculate this. So I've written this in full rather than using sort of symbols and then labeling them again. So 1 divided by focal length, which remember we said was the power of the lens, is equal to 1 divided by object distance plus 1 divided by image distance. So the image distance is the one that we don't know. So if we substitute our values in first, and then we'll rearrange. So remember, the focal length is minus 0.33, so we need to include that in the calculation. So let's rearrange to make D the subject. So I put everything to the power of -1 there, but that just means 1 divided by. So we end up with minus 0.1422 meters. I'm going to round this to minus 0.14 meters, which means that it's to two significant figures, which is what the question uses in its values. It doesn't really matter if you use the minus in your final answer, but it's always just good practice too. The mark scheme appears to allow either. So for this question, in terms of marks, you'll get 1 mark for correctly substituting the values into the equation, and a 2nd mark for getting the correct answer. 2 point sources of light are viewed by a normal eye, and their images are formed at the fovea. State, in terms of the active receptors, the conditions necessary for 2 separate images to be seen. Well, first things first, instead of saying active receptors, we're going to call those cones, because those are the things that detect the light in the eye. And that's going to be our first condition, is that those cones are active. And importantly, they need to be stimulated by the light. So that's going to be our first mark. The 2nd mark is going to be for talking about the positioning of those cones and where the light rays are going to hit. Now, think of them as a little bit like pixels in a telescope, in some kind of detector where you've got a grid of detectors, where you have a grid of cones as well. But if those 2 images are formed on the same cone, then they're just going to look like one image, one light source. Even if there were 2 adjacent cones, it might look like just a slightly blurry image or a slightly larger image that covers 2 cones. So actually we need to have an unstimulated cone in between the 2 cones to distinguish this is one image and this is another image, and there's a gap between them. So let's write that down. And that's going to be your 2nd mark. Sound waves are incident on a human ear. Describe how the frequency and amplitude of the vibrations change as the wave is transmitted through the ear to the fluid in the inner ear. Now, really, you could answer this question completely separate from the ear itself, and just talk about how waves typically behave when they cross boundaries. If you picture, for example, light traveling from air to glass, air to water, for example, its frequency never changes, and that kind of gives rise to any kind of refraction effect. If you picture the wave striking the surface, there are pulses which occur at a constant rate, constant frequency, and the rate of those pulses hitting the boundary on one side is going to be the same as the rate of pulses leaving the boundary on the other side, and that works exactly the same all the way through that inner ear. So the first thing we're going to say is that the frequency does not change, and that's going to be our first mark. Remember, we don't need to explain why the frequency doesn't change, it's just a describe question. So your 2nd mark is going to be to talk about the amplitude. Now, again, we could explain this in terms of other physics, namely simple harmonic motion and how oscillations behave. The oscillations are being damped all the way through the ear, which means that the amplitude is going to decrease. The damping is going to remove energy from the system, but you don't need to go into that much detail. You just need to say that the amplitude is reduced as the vibrations travel through the ear. And that's going to be your 2nd mark. Explain how the components of the ear act to amplify the pressure changes due to the sound wave. Now, there are 2 mechanisms at play here. We're going to talk about both of them, but first of all, I'm going to draw a diagram of the ossicle in the ear. Now, this diagram is very simplified, but can you kind of see how on the left-hand side, this shape of structure, this set of bars in the middle, is much longer than it is on this side? Now, the reason for this is we get a kind of lever system going on, where on the side where the force is exerted, the lever is much longer, and then we get the same moment about this point around the pivots. And from that same moment, we actually achieve a larger force on the right-hand side oval because the length of the lever is shorter. Obviously, this is a very simplified diagram. What you need to say for your answer is that the lever from the ossicle produces an increase in force. And there's your first mark. So for the second and third mark, we're going to use the pressure equals force divided by area equation. And using a change in area with a constant force, we're going to get a change in pressure. So let's put that into words. So the eardrum has a much larger area than the oval window. That's another mark. And then the last mark is going to be to mention this pressure equals force divided by area equation. If you imagine the area changing, getting smaller, then what that's going to mean for a constant force is this fraction overall is going to get bigger because it's got a smaller denominator. So actually the pressure will be much higher. And that's your third mark. So decrease in area with a constant force, increase in pressure. A sound intensity meter set to the dB scale, which is the decibel scale, is placed near to a source of sound. The intensity level reading on the sound meter is 82 decibels. Calculate in watts per meter squared the intensity of the sound at the meter. Now, there's an equation that we're going to use for this. It uses logs. We write that down first of all. Now, interestingly, you don't get a mark for quoting that equation. The mark scheme is more interested in the values that you're quoting because you need to have a value for I0. You need to know what to do with those numbers. And then obviously one of those marks is going to be for getting the correct answer at the end. So let's first of all put in the values that we know, and then we'll rearrange. So we know that the reading in decibels is going to be 82. And we know that I0 is going to be the intensity threshold for hearing, which is going to be 1 times 10 to the power of minus 12 watts per meter squared. And that's just a value that you need to know. So we're going to rearrange to make I the subject. So I'll do this in a couple of steps. Firstly, let's get the log to base 10 on its own. So what this means then is that 10 to the power of 8.2 is equal to whatever's in the brackets of the log. So let's write that down. And then finally, we'll multiply both sides by 1 times 10 to the minus 12 to get I on its own. And that should give us a value of 1.58489 times 10 to the minus 4, which we're going to round to 1.6 times 10 to the minus 4 watts per meter squared, because the value that's given to us in the question is to two significant figures, so we need to make our answer the same. So in terms of marks, as I said, this is more about values. So the first mark that you're going to get is for correctly quoting that hearing threshold, which is going to be 1 times 10 to the minus 12 watts per meter squared. The next mark is going to be for multiplying that by 10 to the power of 8.2. And then the last mark is going to be for getting the correct answer, 1.6 times 10 to the minus 4. So 3 marks. The sound intensity meter is 2 meters from the source, which is emitting sound equally in all directions. Calculate the power emitted by the source. Now, this question is similar to how you might calculate the power outputs of a star based on an intensity of radiation that it receives at a certain distance. Remember, it obeys the inverse square law. But what this is actually saying then is that at a distance of 2 meters, we're getting 1.6 times 10 to the minus 4 watts for every meter squared of area at that distance. Now, the area at that distance is going to make up a sphere because it's emitting outwards in a kind of spherical wavefront. So first of all, we want to calculate the surface area of a sphere of radius 2 meters. I won't calculate that just yet because we can substitute that into another equation, which is going to relate power, intensity, and area. So actually, if we're calculating power, we're going to need to multiply this area that we've just calculated of this surface by the intensity that we obtained in the previous question. Because by obtaining that area, we've got the total area that's detected that encloses that source of power. We know that each meter squared of that area is 1.6 times 10 to the minus 4 watts. That's what that intensity means. So we're just scaling that up to include the entire area. So we're multiplying the intensity by the area to get the power. So we've got that intensity, 1.6 times 10 to the minus 4, and the area that we've just substituted, put together. So that gives us 8.0425 times 10 to the minus 3. And then we're going to round that to 8.0 because, again, the question has given us a value to two significant figures. So we should give a value to the same number of significant figures. Notice how each time I'm almost quoting exactly what the calculator says, giving it to a much larger number of significant figures, just so the examiner knows exactly where you've got your number from. So 2-mark question here. The first one is going to be for correctly calculating the power and making the correct substitutions. I'd have thought that would be for just calculating the area, but they actually want you to get to the power bit before they give you that first mark. And then the second mark is going to be for correctly getting 8.0 times 10 to the minus 3. So 2 marks there. Positron emission tomography, or PET, and ultrasound scans are both used in medical diagnosis. Compare the quality of the information obtained from these scans in terms of patient safety and convenience, and information available to the doctor from the images. And this is a 6-mark question. There's lots and lots of info that we can include to compare these two methods of imaging. We're going to talk through them and put them into a clear, concise format so the examiner can read it and award 6 marks for it. Now, this isn't going to be as simple as 1 mark per point because there are going to be more than 6 points that we can make. Also, things like quality of written communication play a factor here. So if your spelling and grammar aren't good, then you could lose a mark, which means that actually, in terms of the key information itself, there might only be 5 marks up for grabs. So it's not as simple as just 1 mark per point made. So let's start with patient safety and convenience, and we'll write advantages of one versus advantages of the other comparison table. So firstly, an advantage of ultrasound is that there's going to be no exposure to ionizing radiation. Whereas for a PET scan, obviously you're going to be exposed to gamma rays. So let's put the equivalent for PET scans on the left-hand side. So another thing to say about ultrasound is that it takes far less time to do, perhaps between 10 and 15 minutes. So again, another advantage for ultrasound. Another thing that you can say is that you need an injection for a PET scan to get the radio-labeled glucose into the bloodstream. Now, in terms of where this scan takes place, for a PET scan, you're in quite a confined space. It's not very good if you're claustrophobic, but also you need to keep still. So it's not too good for children, for example, especially if it's for 2 to 4 hours. Whereas for ultrasound, you're allowed to move around. You do require kind of a cold gel that's put on you to match the impedances, but actually that's much preferable to lying in a confined space for 2 to 4 hours. So that's all there is to say about safety and convenience. Let's have a look at information available to the doctor from the images. So this is where the advantages for PET scans come in, because you can get a lot more information rather than just an image of sort of shadows, if you like, based on how the sound waves are reflected back or how the ultrasound waves are reflected back. We can actually tell which parts of the body use certain chemicals at certain times because we can use different radio-labeled chemicals. So an example of that could be if you were to use radio-labeled glucose, you could put that into the bloodstream, and then something like the thyroid, which uses glucose, you could determine sort of healthy function or unhealthy function based on that. Now this is where ultrasound falls behind a little bit, because actually you can only work out the size and position of something, such as a fetus. So different purposes given to those scans. Now, if we focus in on the brain for a second, PET scans are good for examining the brain because you only need to insert a chemical into the bloodstream which is used by the brain. And as long as that's radio labeled, you'll start to get positrons emitted from that chemical within the brain, and you get that annihilation process that produces gamma rays, which can then be detected. So it's good for brain function. However, what you can say for ultrasound is that you can image soft tissues quite easily. So it's still useful in that sense. The last thing to say about PET scans is actually you can work out whether tumours are malignant or benign based on their sort of structure and so on, whereas ultrasound can't give you information as detailed as that. you won't be able to distinguish between benign and malignant solid masses, only the shape and position, size, as we said before. So lots of information here. As you can see, there's a lot more there than is needed for 6 marks if you were to count the number of points. But like I said, it's not exactly 1 for 1. So let's just say, first of all, that you'll get a mark for your quality of written communication. Now, technically, you could break down patient safety and convenience into 2 separate areas, one for safety and one for convenience, but I've included them all into one here. But on that basis, if you did split that into 2, you could have 3 separate sections. To get all 6 marks, you would need to cover all 3 of those sections fully. If one of them was only partially covered, for example, then you would lose a mark. If one section was missed out, for example, you might lose 2 marks and then have to rely on the others. So it's more about detail given to each section rather than number of points made. But further information on that can be found in the mark scheme. Explain why the effective half-life of a radionuclide in a biological system is always less than the physical half-life. Now, obviously there's an equation that governs this, but we're going to come to that a bit later on. Let's think about what we mean by effective half-life. Now, this is the half-life of the radionuclide when there are other factors considered. For example, what the body of the person in which the radionuclide is injected actually does to that radionuclide. Namely, it will excrete the chemical. It will remove it from the system. So on that basis, it's going to have a combined half-life, partly due to the decay constant of the radioactive substance itself, but also the rates of removal of the body. So we're going to call that just biological removal. So the physical half-life, depending on which radioactive substance we use and its physical properties, and then we're going to talk about the effective half-life is going to be after biological factors and excretion have been considered. And if we've got something that's going to be in the bloodstream for several hours, there are plenty of metabolic processes which could remove that chemical. So we've made 2 points here, we're going to get a mark for each. The physical half-life of a radionuclide is 20 days. The nuclide was administered to a patient. Initially, the corrected count rate at the patient's body was 2,700 counts per second. 5 days later, the corrected count rate at the same place on the patient was 1,200 counts per second. Calculate the biological half-life of the nuclide. So it's a 4-mark question, plenty to do here, several steps, and then at the end of the question, we're going to get a value in days. Now, the physical half-life is already given in days, so there won't need to be any time conversion made there. So the marks will be allocated elsewhere. Let's first of all write down the equation relating the effective half-life to the physical half-life. So I've written there 1 over TE is equal to 1 over TB plus 1 over TP. And let's label that to include the half-lives. So we've got effective half-life, biological half-life, and physical half-life. Now we're given the physical half-life already, so we could just put that straight into the equation. We need to work out the biological half-life. We need to work out the effective half-life using this 2,700 counts per second and then 1,200 counts per second. So we're going to use the exponential equation for this. So I put AT is equal to A0 e to the minus lambda t. Let's just label that. So we've got the activity at a given time is equal to the initial activity multiplied by e to the power of minus the decay constant multiplied by time. Now, we're given the initial count rate, which is proportional to the activity, so we could just use count rate in this equation anyway. And we're given the count rate 5 days later, which is going to be 1,200 counts per second. So let's substitute the necessary values into the equation to find the decay constant, and then we can use the decay constant to find the half-life. So the count rate after 5 days, 1,200, is equal to the initial count rate, 2,700, times e to the power of minus 5, so 5 being the time in days at which this occurs, multiplied by the decay constant, which is lambda. So we're going to rearrange this to make lambda the subject. So I put an intermediate step there, minus 5 lambda is equal to the natural log, or log to the base e, of 1200 divided by 2700. So lambda is equal to minus 1 over 5 times that same natural log. What you can do is substitute this into the effective half-life equation, or you can just calculate it outright and use that value. Just be careful not to truncate the value too much, or i.e. use a number of significant figures which is too small, because you might get the wrong final answer and we don't want that. So this lambda will be 0.1622. Now be very careful not to put this directly into the effective half-life equation, because you may lose a mark. We need to first of all use this value of lambda to work out the half-life. So the effective half-life is equal to natural log of 2 divided by the decay constant. So we end up with 4.273 days for the effective half-life. Now what we need to do is put that into the equation and rearrange. So 1 over the effective half-life, 4.273, is equal to 1 divided by the biological half-life plus 1 divided by the physical half-life, which remember was 20 days. So let's make T be the subject. So we've got 1 divided by 4.273 minus 1 divided by 20, all of that to the power of minus 1, i.e. the reciprocal, 1 divided by the difference between those fractions. And that gives us 5.4340 days, which we're going to round to 5.4 because the values given in the question are to two significant figures. Now, in terms of where the marks are allocated, the first mark will be for correctly substituting the values from the question into the exponential equation. Your next mark will be for calculating the decay constant, this value of lambda. Your third mark will be for correctly substituting the values into the effective half-life equation. And then your fourth mark will be for correctly getting 5.4 days at the end. So 4 marks there. Table 1 gives the properties of 2 radionuclides. Now we've got technetium-99m and iodine-131, and they're compared on emitted radiation, half-life in hours, and the energy of gamma rays in kilo-electron volts. By considering information in Table 1, suggest which of these nuclides is more suitable for use as a tracer in medical diagnosis. It's a 4-mark question. Now, the way I would approach this question is to draw a table. So I've got a column for different factors. I've then got the comments which can be made about that factor, comparing the two tracers. This is where the marks are going to be scored. And then on the right column here, we've got which of the two tracers do we prefer as an outcome of our comments on each factor. And then I've left a line at the bottom just to make a quick conclusion, for which a mark can be obtained, but we can get 4 marks actually for just writing 4 strong points comparing the two. So the first factor is going to be ionization. So the comment that we're going to make is that beta is much more strongly ionizing than gamma. So iodine-131 is going to do more damage there because it emits beta, it's more ionizing. So in this case, we would prefer technetium-99. The next factor we're going to compare them on is energy. And the thing to note here is that the gamma rays produced by iodine-131 are more than 4 times as energetic as those for technetium-99m. So that's going to be difficult when using a gamma camera. They're not necessarily going to be as easy to detect. So that's going to be a point in favor of technetium-99m again. Just going to give myself a little bit more space there to fill the table in. So the next point is going to be on half-life. So iodine-131 remains in the body for too long. It's got that half-life of 190 hours, which is much longer than 6 hours. Could cause harm to others, but I suppose it could cause harm to the patient themselves as well. So again, technetium-99m preferred in that case. Now the last point I'm going to make is going to be on half-life again, but actually a downside of the half-life of technetium-99m being that it could be too short for the appropriate image to be taken. So on that basis, it may be that we prefer iodine-131. So on half-life, it could actually be a tie. There are pros and cons to both. But as you can see from the overall table, it would be preferable to use technetium-99m. So that's what you're going to put in your conclusion. So in terms of marks, you can see I've made 4 points in this table, 1 for ionization, 1 for energy, and 2 for half-life. Each of those will give you a mark, but then you could also get a mark for making a suitable conclusion at the end. Now, I'd imagine if you were to just write technetium-99m is more suitable on its own without any of the points made in that table, you probably wouldn't score any marks, because on that basis it would just be 50-50, one or the other, and the examiner doesn't really like you putting things down to chance. You need to prove that you know why it's technetium-99m. So your 4 marks could be a combination of 3 points made from this table and then that conclusion at the end, but 4 marks maximum.